So what I'm going to do today is, first of all, pick up where we left on Thursday. Uh, for those of you who were there, we started with a collection of questions, mainly from actually solely from the 2014 uh, exam, excluding some of the questions that were not relevant at all. And I went through most of them, but we ran out of time before reaching the question 12. And I'm going to just pick up from there, try to finish uh, 2014 exam, and then move to 2013 and see how much of it we can cover today. And again, on Monday, right before your exam, we're going to have another recitation. So if you have any question at that time, if you have any question, you can express it right here or keep it for Monday. Now, so from fall 2014, 15, is it 14? 14. So we covered everything, reached the question 12. Hopefully you can see the arrow, the green arrow that is here. So I can actually move it around to show you stuff, so that's pretty good. Now, which statement is well supported by the phylogeny shown below? So the phylogeny in question, there are a number of flowering plants related to each other. A, M. cardinalis, which is the first one here, and M. Parishii, which is here, form a monophyletic group. Is that correct or not? So we can just, if I could draw, that would be great. So they're talking about these, this one and this one, right? So these two. So what type of group is that? So as you can see, we have M. cardinalis, M. Parishii in a single group. If you were to construct that group, what kind of, how would you describe it as far as the phylogeny is concerned? So what we have is two taxa, and there's another taxa between the two. So M. luisi, which is the sister taxa of M. cardinalis. So this one, M. luisi. So this group, the M. parishii, M. cardinalis group, cannot be cannot be cannot be a monophyletic group. So can anyone hear me actually? So Shmita told me that she can't hear. Hopefully she can hear right now. Okay, that's the problem has been rectified. Now, so these two groups, cardinalis and parishii, there's a sister taxa excluded from the group. So Hossein also reassured me that my sound is fine. So these two groups, this one group, including these two species, excludes the sister taxa in question, M. luisi, so it can't be a monophyletic group. So we know that the first one is not right. The second one says M. eastwoodii. So where is eastwoodii? So they use a different color. So here, M. eastwoodii is more closely related to M. cardinalis than to M. nelsoni. So M. nelsoni is here, M. cardinalis is there. So is it closer to nelsoni or cardinalis than to nelsoni? So in the case of cardinalis, so there is, so from Eastwood, there's one common ancestor, second. So what I'm trying to do is to count the number of internal nodes. So by internal nodes, I mean these points So like this one is an internal node. This one is an internal node. This one is. So internal nodes are simply the ancestors. So the question is, from Eastwoodii to Cardinalis, how many common ancestors I have to cross in order to get from one to the other? So I start from Eastwoodii. There's one common ancestor here. There's a second one here, a third one, a fourth one, and a fifth one. So 5. Well, in the case of Eastwoodii and Nelsonii, there's 1, 2, and 3. So Eastwoodii is closer to Nelsonii because there are only 3 points, 3 internal nodes you have to cross in order to get from one to the other. So this one is also wrong. So B, also wrong. C, the trait of hummingbird pollination. Hummingbird pollination, so red lines are hummingbird pollinations, whereas the black lines are plants pollinated by bees. So the trait of hummingbird pollination has a single origin. So as you can see in this group, so 96, there is, so here. So this common ancestor had the ability, or evolved the ability, to be pollinated by hummingbirds. So that's one origin, but in the case of Cardinalis, we have an independent emergence of the same trait. So the trait of hummingbird pollination does not have a single origin. So this C is also wrong. D, the trait of the red flowers evolved repeatedly. So in the case of, oh god, so which one is, so the trait of red flowers evolved repeatedly? That's, that didn't evolve repeatedly. Oh, okay, sorry, the trait of red flowers, so this one. Oh, so red flowers, so Cardinalis has red flowers, Eastwoodii has, which one's a verbenaceous? Has Nelsoni and rupestris. So there are, so all the groups, all the species that have the ability to be pollinated by hummingbirds, they have, incidentally have red flowers, probably because hummingbirds have color vision versus bees, where they have UV vision, so they can't really, they see colors but not in the same way. As we can see, Cardinalis evolved the trait of having the red flower independent from 96, so that the cluster, including those 4 species, descended from the ancestor 96. So here, so it happened twice, once in 87, sorry, and another time in 96. So the trait of the red flowers evolved repeatedly. That is correct. So D is correct. So any questions so far about this? I think several people are typing, so I'm assuming there is a question at least. Oh, choice C. Joseph says, can I explain? Actually, no. So Sylvia says, can you explain choice C? And so choice C, so the trait of hummingbird pollination has a single origin. So as you can see, so you have here, if you see the green arrow that I pointed at Cardinalis, so you have, so let's delete these things. So just make it, okay. So the green arrow refers to Cardinalis here, right? And Cardinalis is being pollinated by hummingbirds. And the ancestor of Cardinalis and Louisi, which is 87, didn't, evidently, right? So they have the ability to use hummingbirds to spread the pollen, evolved in M. cardinalis here, right, once. And then in 96, so you have all these 4 species that are being pollinated by hummingbirds, and they also evolved it independently, right? So in the case of C, it says that the hummingbird pollination has a single origin. Obviously not, because it happened in 87 and again 96. Hopefully that answered the question. Jennifer says, "Is there an answer key to this and the other previous exams?" No, sadly there's no answer key to those. Question, Joseph. So I've already covered a lot of the questions from. By the end of today, hopefully we'll cover this exam, which is 2014 and 2013 as well. I cover as much as possible. On Monday, I cover the rest. So that would be the answer. Joseph says, "Could you please explain monophyletic, please?" So monophyletic is a situation where so you have this group, right? So there's a species 1 or taxa 1, taxon 1, taxon 2, and taxon 3. So if I say that if I create a group which involves 1, 2, and 3, that will be a monophyletic group, because I include so this gray cross here. So I have so in this group I've included all the descendants of this ancestor, this one. So the green arrow is pointing to that ancestor. So in this group I included 1, 2, and 3, which are all descended from the ancestor here, and I didn't leave out any of the descendants, right? So it's a monophyletic. It's a single phylum, or where all the or it's a single tree where all the branches are descended from the same ancestor, and also I included all the branches, right? So that is a monophyletic versus a polyphyletic situation, or sorry, a paraphyletic would be a situation where if I only include 1 and 3, that would be a paraphyletic because I excluded 2 from the group. So it's only 3 and 1, so I didn't include all the descendants of the ancestor. Hopefully that explained the situation. Now, moving on to the next question. Question 13. Consider phylogeny shown below. Says a phylogeny where we have 3 different traits, and these traits they're all binary traits, so they all have 2 states shown with different colors, right? So for trait 1, blue represents the ancestral state and red represents derived state. Again, if you're colorblind, I do apologize, because they were made without colorblindness in mind somehow, which they should have taken that into account. Derived state. So with respect to trait 1 only, what is the smallest number of evolutionary change that could explain that could have occurred, right? So again, we're going to follow the maximum parsimony, meaning that we are going to minimize the number of changes that should occur. So what I'm going to do, so in this case, so in this group, everyone, these F, G, and H, they all have to change. So I'm going to just put the change there, because blue is ancestral, right? So F, G, and H, they all share the same ancestor that carried the same derived trait. In the case of A, B, and C, just 1 change would suffice. So 2 changes would suffice to explain this tree. So 2, which is B, is the correct answer. All right. The next question, number 14. So we're going to move on to a little bit of Hardy-Weinberg um, uh, situations where you have an expected level of genotypic diversity, and you try to see if the population is in that equilibrium. Oh, sorry. So Sylvia asked, can the outgroup also determine the answer? State absolutely. So that absolutely yes. So outgroup is there to determine the ancestral state, which is in this case out has the blue trait, meaning that that is ancestral. And so that's a reference to question 13. Jennifer asks, will these formulas usually be provided? Absolutely. So they always provide the equations, so you don't need to memorize any equation. You just need to know where to use them. Now, in the case of 14, so a sample from a population of the yeast Candida glabrata was genotype at the RAD16 locus. These are irrelevant information. Two alleles, G and J, G and G, capital G and lowercase g were found. The following genotype counts were obtained. What is the frequency of the G allele? So from the equations, we know that so the frequency of G would be this one, right? So the frequency of P is what they mean. So because in this case there's lowercase g and uppercase G is P and Q, yeah, because it's a binary situation, as usual. So what is the frequency of X? So there is, I actually do have a calculator. It's 12 plus 18 plus 4. So the total population is 13. So sorry, not 13, 34. So we have 12 divided by 34, which is the frequency of uppercase G, capital G, plus 18 divided by 34. That entire thing divided by 2. Right? So what is the answer to this? So 12 divided by 34 would be 0.35. So this one is 0.35. 18 divided by 34 is 52. Or actually 53. 0.53. This 0.53 divided by 2 would be 0.26 plus 35. 0.6. So the answer would be 0.62. So it is roughly 0.62. Okay, so this one. A is the answer to the first part of this question, right? So what I did simply, so it's because I've been given all the equations. What I just needed to do was to understand that I want the frequency of the capital G allele and capital G genotype. So this one. So every allele in this genotype is a capital G, so that entire frequency contributes. Whereas in the case of heterozygotes, capital G, lowercase g, half of them, half of the alleles are capital G, the other half are lowercase g. So I had to just calculate the frequency and divide it by 2. And if I add up the frequency of capital G, and the heterozygotes divided by 2, I get the answer. So just sometimes people make the mistakes in arithmetic. There are problems, so you can't just, so you have to calculate the frequency and then divide, because then you get the wrong answer. And so just these simple mistakes can result in you calculating something incorrectly, even though you know the formula. Now, 15. In the population described in the previous question, what would be the expected number of capital G, lowercase g heterozygotes if the population was in Hardy-Weinberg? So let's go back. What was the P was 0.62, right? So we know P is 0.62. Q is 1 minus that, right? Which is 1 minus 62. I can't do mental math. 0.38. Right. And what was the? So the question is, what's the expected frequency of heterozygotes? The frequency, I'm going to use F to denote frequency of GG. The expected one would be 2 multiplied by P multiplied by Q, which means it's 0.38 multiplied by 0.62 multiplied by 2, which is 0.47, right? So that's the frequency. Now that's so the population size was 34. So if you multiply that by 34, you get 16. So 34 and 16. So the expected number of heterozygotes in the population, if the population was in Hardy-Weinberg, would be 16. In reality, it is 18. Right. So how did I calculate the expected frequency of heterozygotes from the frequency of one of the alleles, and then I just calculated it. So that was pretty simple. So imagine that the population described in the previous two questions experiences a strong migration of capital G individuals over several durations, assuming that otherwise the population meets the conditions of Hardy-Weinberg equilibrium. How would you expect the frequency of the G allele to change as a result, relative to the value calculated in question 14? So there is a strong migration of capital G. I'm assuming they're just moving in. So if you have more heterozygous than homozygous, what happens? What happens to the allele frequency? So anyone, any suggestion as what will happen? So the question says that assuming that the population is at Hardy-Weinberg, right? So let's draw a ternary plot, right? So you have GG, G, and then you have right, and there's an equilibrium here, and the question is when there's a strong migration of capital G, so you just pump capital G individuals into the population. So to talk about the allele frequency, so allele frequency, since it's a neutral equilibrium, it can change. So it's not really resistant because it's not a stable equilibrium. It's just a neutral equilibrium. So you can change the allele frequency without a problem. So how would it change though? Okay, let's assume that it happens, right? So in the case of, I would say it would increase a little bit, but so it will increase. I mean, it's a neutral. It is a neutral equilibrium, so it should change. But let me add a caveat, is that for it's probably better to calculate. So what I mean by that is that since it's going to take time, I do it on. So someone actually reminds me on Monday to do it. So just to calculate if it changes or not. I'll try to remember that. But so this one. So this question is probably it will increase, but I'll try to calculate it on Monday to see if that's the case. And again, just to remind you, the reason is because allele frequency is neutral frequency, so it should be able to change it as opposed to genotype frequency. So I know it's neutral because it says so. So yeah. So if so, what does it mean to be neutral? It means that if I start these Hardy-Weinberg simulations and I set the allele frequency at some value, it's going to stay there. If I change it, it's going to stay in the changed value as well, right? So if I show it with a time series, so it's time shown by T, and so this is the allele frequency P. What I mean by neutral is that if I start from here, it's going to stay there. If I start from here, it's going to stay there. If in the middle of simulation I change it to here, it's just going to stay in the new value, right? So that's the neutral equilibrium. Is that it is like a marble ball on a piece of paper. There is no real push and pull. It just, if you move it to one position on the paper, it's going to stay there. On a paper or on any flat surface. So again, just remind me on Monday to check this. Oceanic islands, I think that's one of the questions in the essays, so I'm going to avoid that. 18, how would you summarize Paley's argument from design? So just to remind you, William Paley was a theologian. He wrote a book called Natural Theology, and he talks about the fact that his argument was against the idea that it's conceivable for any complicated entity to be to evolve. In his idea can be summarized as that biological systems are complicated like a watch, and so they must have been designed because something that complicated cannot just appear, right? So that's Paley's argument. Okay. Question 19. Consider the following figure. How would you summarize it? So as you can see, there's an owl on the top left. So here, there's the owl, and there's an ostrich here. And on the x-axis, there's the total field of vision. And the y-axis, there's the range of binocular vision. And as you can understand, the total field of vision means the area in front of you and around you where you can see without moving your head, that is. And the binocular vision is the 3D perception of depth. And as you can see, while owls have a higher range of binocular visions, they have much lower total field of vision, right? So they are on the upper left, while ostriches, they have a higher or a wider field of vision while lacking the binocular vision. Owls have, so they're on the lower right. Now, A, the ostrich has the eyes on opposite sides of the head, therefore it has a wide range of binocular vision and a narrow total field of vision. That doesn't make any sense, right? Just to imagine, just to understand the reason for it, we do have binocular visions and our eyes are in front of our skull, while cows, they have their eyes on the sides, and they really don't have good binocular visions. So predators, generally, they do have binocular visions, because in order for you to chase the prey, you need to estimate the distance. And in order for you to be able to do that, you need to have a perception of depth, which is required and demands a binocular vision. So A is incorrect. The ostrich has its eyes on opposite sides of the head. That so far is true. Therefore, it has both a narrow range of binocular vision and a narrow total field. That's not true, because they have a narrow range of binocular vision, while they have a wide range of wide field of vision. C, the ostrich has its eyes side by side in the front. That's already wrong. The owl has its eyes on opposite sides of the head. That's not true. So E, the owl, so it should be true, because that's the last one. The owl has its eyes side by side in the front of the head. Therefore, it has a wide range of binocular vision and a narrow total field of vision. This question simply wanted to make sure that you can read a plot. So if you could really understand the relationship between two parameters across two axes, so total field of vision and binocular vision, you could have responded correctly responded to this question. 20. The figure in the previous question illustrates what concept? So it's convergent evolution. That can't be the case, because owl and ostrich, they show different traits. They have different level of different levels of development in regards to two different traits. Synapomorphy, shape-derived trait, obviously not. Trade-offs, which is the trade-off, because the idea being that evolution can either increase the range of binocular vision or the total field of vision. You can't have both, so it is a trade-off. Vestigial structures, none of these are vestigial, they are totally functional. And none of the above, that's also not the case. So the last one is also similar to essay questions. So I'm going to move on to 2013. So any questions so far? I just need to find that PDF. 2013. The PDF is. Well, I actually, Jennifer asked if I can provide the answer from the first half of the exam. I really don't remember, but people who came to recitation on Thursday, they actually do have a printout of this, and you can just ask them to give it to you. If everything failed, I can help, but I think it would be easier for to just ask anyone who showed up, and there were a few people who showed up, so it should be easy, relatively easy to find someone. Now, the 2013, I think it was it. I was talking about the one question being excluded. Was it the third one? Anyhow. So question one, you study a population of mice over several generations, and you observe that body size decreases steadily over the period. The condition must be met for that to constitute an example of evolution. So the idea being that the definition of evolution, which is the change over time within a population, that is a necessary condition, but it's not enough for that change to be considered an evolutionary change. So A says larger mice must have higher fitness. B, smaller mice must have higher fitness. C, resources must be limited. D, the change in body size must be caused by environmental conditions. E, the change in body size must be caused by genetic or epigenetic changes. So which one would be the case? So the question, so the idea is that there should be differential reproductive success, right? Meaning that there should be fitness associated with traits that are heritable. So heritability. So if the changes are caused by environmental effects, which is D, that can't answer the question, right? Resources be limited, that also doesn't make it a differential reproductive success. E, the change in biases must be caused by genes. So there's a genetic component to it, so it's heritable. Right. So in the case of A and B, you still don't know if they're heritable. So you can have traits that affect the fitness. But if the changes are not heritable, so if larger mice produce offspring that are randomly, they have random size associated with them, then it doesn't make sense for evolution to select for larger mice or smaller ones, depending on the demand of selection, right? So in order for evolution to work, you need to pick someone with a specific trait, and you need to be sure that there is a high probability that the offspring of that individual would carry the same trait, or traits correlated with the parental trait, so you can steadily change the population. I think question 2 is not relevant to what we do, so that's fine. Question 3, which of the following is a component of modern theory of evolution? Life on Earth evolved gradually, beginning with one primitive species. Life evolved gradually from several species, rapidly evolved or not evolved. So those that say rapidly, they're already wrong, right? Because the gradual nature of evolution is a major component, or one of the main components of evolution as we understand it. E is also intelligent design stuff. So it's between A and B. One primitive species is what is generally considered to be the case, although it is really not that important, the fact that there was one species. Probably one or a few, that would be fine. 4. The evolution of a bone was a major event in the evolution of vertebrates. So without bone, vertebrates would not have later taken up life on land. Bone has two main functions in extant vertebrates. First, support protection. Let's just underline this. So there are two functions. There's two main functions: support and protection, and storage, homeostasis of certain minerals, including the phosphate ions. The ions of vertebrate bones are in equilibrium with those in the tissue, fluids, and blood that participate in important metabolic activities. If the support protection function evolved after the storage homeostasis function, bone would be A for support. So what it says is that bones evolve for support and protection, and then so they evolve for homeostasis. So let's just number these. So, so first homeostasis and storage happened. So it's 1. That's the 1, and then they started being used for support and function. Right? So in that case, given the scenario, what would be the how would you describe the evolution of bone apropos support and protection? Is acquired characteristic, adaptation, exaptation, maladaptation. So it's an exaptation, right? Because exaptation, the difference between exaptation and adaptation being that adaptation you select for, so there is a trait, let's call it A, you have selected for that trait, so selection, just S, and this is still A, so you still you use the same trait, but in this case you can have initial state A, which was selected for that, but now there is A and there's another function B associated with it, so that one is exaptation. So the second one. Right? Any questions so far? So again, there's just a simple difference between being selected for something and functioning relative or functioning for that. Jennifer asked what was the answer for 1 and 2, 1 and 3. So 1 was E, 3 was A. Question 5. Which of the following is required for the operation of natural selection? Constant environment. Is that required? Not at all, right? That is not required. Inheritance of acquired characteristics. We talked a lot about the fact that that's not really relevant. Inheritance of phenotypic variation, recombination, not necessary. Unlimited resources, not necessary. Inheritance of genotypic variation then is. So there should be differential reproductive success, as I have repeatedly said. So C is the right answer. 6. Which of the following ideas influenced Darwin in developing his hypothesis? As Lyell's ideas on changing geology is the answer. So again, he was really influenced by the idea that Charles Lyell introduced the idea that that processes that shaped the planet and eons ago, they still operate and they are actually pretty slow. So there's a gradual change that happens over millennia, and that results in catastrophic changes. So you end up with a mountain rising from under the sea, but for it to happen, which is quite a drastic change, you need millennia to pass. Question 7. Which of the following does not limit the effectiveness of natural selection? Does not limit the effectiveness of natural selection. The laws of physics. It's actually from the beginning. So changing environment, high level of genetic variation, low so changing environment does not necessarily limit the selection. High level of genetic variation actually is beneficial to selection, because if you are selecting for something, let's say height, if you had people with varying degrees of height, you would have an easier time picking people. I mean, again, that's not an ethical experiment, but just for the sake of explanation, you would have an easier time selecting for the trait in question, which is tall, just getting people to be as tall as possible, if you had a wide variety of people with different heights. If you had just a few varieties, you wouldn't have the variation necessary to select for the trait in question. Low level of low level of genetic variation, that is of course a problem that limits the selection, so that does limit it. The laws of physics, they do limit selection, so you can't have a huge beetle like the ones in what was that movie? Starship Troopers. So you can't have big insects because they don't have they have exoskeleton. The exoskeleton becomes heavy disproportionately as you make them bigger. So the biggest insect was a type of dragonfly. It was like 30 centimeter long, so that way it is long. And that existed when the level of oxygen was 30% in the atmosphere. So that was the maximum. So that's an example of physical laws really limiting the possibilities. In the case of trade-offs, the example we just went over, in the case of owl and ostrich, you couldn't have proper binocular vision with a wide field of view. So that was a trade-off that limited the effect of selection. So C is the right answer for question 7. 8. The following graph summarizes the results of an evolution experiment using E. coli. You are quite familiar with that experiment. Actually, we went over this one in the recitations as well. So the red line shows the growth rate of the ancestral population, several temperatures. So this one is actually the one we went over, I think one of the homeworks, where you have this phenomenon of, so I have the blue line being the evolved lines, so they started with 12 lines, and the red line being the ancestral ones. And as you can see, in a wide range of temperatures, evolved ones are actually much better, but then in the extremes, they are worse than the ancestors. And the question was, why? How could that happen? So let's go over the answers. So the 12 populations evolved to grow faster, 37 and all the other temperature. That's not true. The populations evolved to grow more slowly at 37. That's not true as well. So the 12 population evolved to grow faster at 37, but more slowly in the extreme temperatures. So that's the case. So C is the case so far. Let's go over the rest. D is the 12 population evolved to grow more slowly. That's wrong as well. The 12 population did not evolve in growth rate. E, that's not true as well. So H, the answer is C. Question 9. Consider the following tree of holometabolous insects that undergo complete metamorphosis. So there's a bunch of insects. The question is, which of the following groups is monophyletic? Okay, let's go through all of them. So the first one is Mecoptera, so it's this one, Diptera, this one, and Trichoptera. Is that a monophyletic group, right? So these three. Is that monophyletic? So we have, so does anyone know if that's monophyletic or not? So these three, so the three red lines represent the group suggested in the first multiple choice question A. No, right? So that's not a monophyletic group because Siphonoptera has been excluded and also Lepidoptera is excluded. So this is not monophyletic. Okay, let's go. What's the next one? Diptera. So Diptera, actually, they're termites. And Lepidoptera, they are butterflies. So Diptera, Trichoptera, and Lepidoptera. So is that a monophyletic group? No, as Ryan points out, absolutely not. Again, the reason being that the common ancestor of Diptera, Trichoptera, Lepidoptera is here. So the red cross, and as you can see, if we create this group, Siphonoptera and Mecoptera, they are excluded, right? So that is not also a monophyletic group. C, Lepidoptera, Coleoptera, and Strepsiptera. So is that a monophyletic group? Jennifer says no. Christine says no as well. So that should be the right answer. All right. D, Neuroptera. Where is Neuroptera? Okay, Neuroptera, Rhapidoptera, and Megaloptera. Is that a monophyletic group? Yes, absolutely. Christine, Jennifer, and Ryan, they got it right. So this is, I think all of you probably have guessed this one is the right one. So the D is the right answer. So now we have, although this is not a resolved taxa, So would answer choice B be a paraphyletic, or so B was Diptera, Trichoptera, Lepidoptera. So that would be a paraphyletic, I would think. Justin says in the case of B, so in the case of B, we had these three. So Diptera, Trichoptera, and Lepidoptera, and he says that if that's paraphyletic or polyphyletic, that is a polyphyletic group because we excluded these two as well. So it's still, so you have some of the descendants of the common ancestor of Trichoptera and Lepidoptera, so these two, and one descendant of the ancestor of Diptera, Mecoptera, and Cephaloptera. So it's paraphyletic, I would say, to Justin and Jennifer. Paraphyletic. Question 10. Which of the following kinds of mutations is least likely to be deleterious? Deletions. So deletions, they are not likely to be, they are likely to be deleterious because you are deleting. And usually you can't just delete the stuff from a functional entity and expect it to function properly. Again, I would usually use the example of a computer. If you open a laptop and remove components from the board, it's more likely to malfunction or die entirely than operate as usual. So this is not that is A is likely to be deleterious. Missense mutations are mutations that are, you substitute one amino acid with another. So let's say a missense would be glycine replaced by alanine, something like that. So it's a different amino acid that can be, that is usually deleterious, or can be. Nonsense mutations are mutations where you have, okay, let's say more space. So nonsense ones, let's say this glycine is now replaced by stop codon. So that results in a truncated protein. It doesn't function, so that's also not true. Silent or synonymous mutations, by definition, they are likely to create this, to result in the same phenotype because they are silent. That's their definition. So for question 10, it's D. Let's go over at least two more questions before we call it. Which of the following statements about the hypothesis of blending inheritance is the most accurate? In the 19th century, most biologists believed in BI, and Darwin showed that it was true. If BI was correct, natural selection would grind to a halt because BI would destroy genetic variants. So it's all right, but except for Darwin showed that it was true, that's not really the case. B, in the 19th century, most biologists believed in BI, and Darwin showed that it was true. So again, Darwin didn't show anything about genetics. Okay, in the 19th century, most biologists believed in BI, but Mendel showed that it was false. So far, it's true. If BI was correct, natural selection would grind to a halt because it would destroy genetic variation too rapidly. So this one is the correct answer. So as you understand, the idea of blending hypothesis being that you combine the traits of parents and you get an intermediate phenotype. The problem with that is that if, let's say, you want to select for tall individuals, again, the same example, and if every time you try to breed, use tall parents to create tall offspring, you just get intermediate offspring, you are not really likely to increase in the, select properly for the phenotype in question. You need there to be variation, and for the variation to be intact so you could select for it, it shouldn't just dilute as evolution, as time goes by. So one final question. I'm going to cover the rest on Monday. Question 12. Laura Delbruck conducted a famous experiment aimed at distinguishing between two hypotheses on the evolution of resistance. Which of the following best describe the acquired hereditary resistance hypothesis? So that's when, so acquired hereditary resistance, meaning that you come into contact with phage, you develop the mutations necessary to combat the phage. So as a consequence of exposure to phage, a few susceptible cells mutate such that they become resistant to phage. Only these resistant cells survive exposure to phage, so that's A. B, as a consequence of exposure to phage, a few cells mutate such that they become resistant to the phage. Both susceptible and resistant cells survive. That can't be the case, right? So B is strong. As a consequence of exposure to the phage, all susceptible cells mutate such that they become resistant to phage. Also survive. That's not the case as well. Prior to exposure, so the prior ones, that's not true, because prior to exposure means that they already had the variation. That's not the acquired hereditary resistant hypothesis. That's the undirected mutation. That's the one that they proved to be the case. So A best describes the best describes this hypothesis. Okay, I think this is done for tonight. So if you have any question, please ask. We're going to have a recitation, as I have told a few times tonight. On Monday, I'm going to finish this exam. Also, if you have any question, please. Jennifer asks, no, it's not remote, it's on campus. It's what time is it though? Is it? It's 1 to 2, I think. Yes, 1 to 2. The address and time are all available on Blackboard. Yeah, I've been. Thankfully, everyone knows where it is and the time. So, so at the same time, the same place on Monday, we're going to cover everything from this exam. And if you have any question, just bring it there. I'll answer it. Of course, I can't answer the essay questions, but any other question and related stuff I can talk about. Probably we will not cover the homework because the homework is not going to be relevant to your exam. We'll just cover the homework on Thursday. All right, and any question before we conclude this recitation? Jennifer says, I thought the mutation already existed in the cells. Well, Jennifer, that is the correct hypothesis, but they had an alternative hypothesis, which was the idea that the mutations would arise as a product of the presence of phage. So that was a directed mutation hypothesis. So they just disproved that. Wajahat says, can you explain why 7 is C, not B? Let's go back to what was 7. Where is 7? So Wajahat asked, why is 7 C and not B? So B means that if there's high level of variation, selection high level of variation should not limit selection, because it's just easier for selection to work if there is a lot of variation. So imagine again in the case of pigeon fanciers, right? If you are looking for a specific combination of plumage color, like you want a purple plumage with some burgundy in it, and if there is no variation in the plumage color in the population, you can't select for that, right? So that would limit the effectiveness of your selection. So that in that case is artificial selection, which works in the same way as natural selection. So low level of genetic variation would result in would limit natural selection. Oh, so, sorry. Yes, yes. Okay, sorry. So I actually I am sorry. I explained it correctly, but I picked the wrong. So high level of genetic variation does not low level of genetic variation. Sorry, I do apologize for this. Okay, so B then. Okay, so question 7, the high level of genetic variation. So Dipankar is right, and thanks Wajahat for also pointing that out. I do apologize for that mistake. I mean, my explanation was true. I stand by the explanation, but I picked the wrong answer in the frenzy that was the middle of the recitation session. So my apologies. Any more questions?